Hello. In a few minutes, I'm going to have a talk at the Google Developer Group in Zurich about why you need to understand the database structures for optimal performance. And I'm Armando Ferrara, and I want just to record this talk for people that couldn't attend this event. And let's start. I hope you like it. So we have a plan for this talk split into part A, database internals, part B, why you should know that. So let's start from part A, database internals. We have here a table with the most dangerous zodiac signs. I'm sure you have seen many times a table. In this case, you have first row, second row, and in other cases as well, and different columns. And in this case, the first row is Virgo with rank 1, so it's the most dangerous zodiac sign. And this way, the rank is even the primary key. So in a row-oriented database, the way you store your row is not that you store your row by row on your disk, but you store your rows inside one page, and those pages are stored inside one data structure called heap that is stored on your disk. The reason why you don't store row by row, but in multiple rows inside one page is because you get for free different rows, and this is quite useful when you are doing like select a range of queries. Like in this example, if I'm selecting where I'm selecting a rank from 1 to 3, I just have to retrieve page 0, and I get for free other 2 rows, and I don't have to retrieve other pages. In this way, I reduce the amount of I/O. In a computer architecture, when I do a select, before processing the data, I have to retrieve them from disk and put in memory if I don't have the data there. Before processing them. Now in this example, we are assuming that we have no index, and if I do a select star from that table where the sign is Capricorn, I visualize that the Capricorn is in page 2, but the computer doesn't know where is the Capricorn, doesn't know that it's in page 2. So doesn't know it because I have no index. So first I retrieve page 0, I bring to memory, and this is one IO. I bring to memory page 0, I scroll all the rows inside page 0, I see if Capricorn is inside, it's not, so I retrieve page 1, another IO, I bring to memory, is Capricorn there? No, so I retrieve page 2, I see that now Capricorn inside page 2, and I can return it. So you see, for a select, essentially I did what we call in Jargo a full table scan. So I scan all the elements, all the pages inside my database. And this is extremely expensive. Think that what database creator tries to do is like, do you remember when there was this game, The Floor is Lava, that became quite famous on social networks? They do the same, just that it's not that the floor is lava, but the disk is lava. Why the disk is lava? Because comparing the performance to accessing disk is like versus comparing the performance to accessing memory is like comparing a F-18 Hornet that goes to roughly 2,000 kilometers per hour. That is your memory, your RAM, with a banana slug that goes 8 centimeters per minute. So you see the difference of access from memory to disk is huge. So you can see the database as main goal, obviously the database that ensure in the ACID properties durability, because you can keep everything in memory like Redis does. But in most database where you want to persist your data, you have to think that the goal is to minimize the searchable space. In this way, they reduce the amount of I/O to find your rows. If they reduce the amount of I/O to find your rows, you can have more complicated queries that bring together more data and create more relation. So they usually use a data structure that is called B-tree and a variant B+Tree. And I don't want that to understand the algorithm itself. I want just that you visualize it because it's useful for what I'm going to tell next. So in a B-tree, we have an element, and an element is composed by your primary key, that in our case is the rank. You can see it's 1, and that page that is the internal data pointer. So I know where this row in what page is stored. So I can do one IO retrieve this page. You can index based on different elements, but let's assume now we are indexing based on the primary key. And you choose maximum degree that in our example is 3. Usually you don't have to do that. It's the database that the underlying database that does for you. And what does it mean 3? Does it mean that to keep the 3 balance is that the maximum number of elements that I can have in a node, so the maximum number of reference to rows is 3 minus 1, and the maximum number of children is 3. By the way, I want to just let you visualize that. You see now we are assuming that the inserts are coming sequentially. So now I have page 4, now page 5 is coming, and I need to split the node. You see, usually I pick the element in the middle. So 4 now goes on top at the root node, and the root node now has 2 elements. I have 3 children, and again, now, just that you see that, because this is going to be useful for when we are going to talk about PostgreSQL. You see, I have now page rank 7 that came. Rank 7 came, and now I have to pick the 6 that is in the middle in this node. By the way, the fundamental part is that at the moment I do edit a node, I do some I/O, because I have to make this consistent on disk. So I have to flash back to disk. So modifying the node, adding a new element or performing a split, it's I/O. And the second point is that a split can cause multiple I/O. Because you see now I have here the 6 that we cause a split in this node. And after the element 6 goes on top, and on top I already have 2 elements. So this will cause another split on top. So I have 2 I/O in this example with one split that happened in one portion of the node. So just remember, this will be important for PostgreSQL. Yeah, I want just to visualize that, the B-tree, and why it's useful. Let's suppose we want to find rank 5. We start from the root node. Is 5 greater than 4? If yes, go on the right side. If not, go on the left side. Yes, go on the right side. Is 5 greater than 6? No, go on the left side. Oh, I found the node that contains the element with 5, and this refers to page 2. So I just do one I/O, assuming that this B-tree is in memory. Assuming this B-tree is in memory, I just have to perform one I/O because I know where is the page 2. Because I know that the row 5 is stored in page 2. Okay, that's nice, but why should I know that? First of all, let's discuss about database engine. Database engine, a library, it's essentially a library that takes care of the disk storage and the cloud operation. What you see nowadays usually is a database management system that they are built on top of database engine. Database engine, they offer the basic functionalities. After the database management system, go and build and add more functionalities on top. And if you want to start to build your database from scratch, don't do it. Just use a database engine, just read the properties on that and build the functionalities that you would like to see in a database on top. For instance, we have MySQL and Oracle.db that use InnoDB. InnoDB uses a variant of the B-tree that is called B+Tree. After we have, for instance, SQLite that use B-tree. Those are database engine, and they build the database management system that you know nowadays on top. Let's start from a case study. I'm sure you have seen this interface many times. And on the left side, you have the conversation. And once you click on the conversation, you can retrieve all the messages, all the history, all the messages related to that conversation. What I've noticed is that once you click the conversation that happened in the past, you have a random ID in the R. And this random ID is a UUID version 4, because the third part is as a 4 at the beginning. So it's version 4. And after I retrieved the JSON that my browser was receiving, and each message had a random ID assigned as well. So I don't know what OpenAI is using as a database, but in the case they are using something like a relational database, or even something like MongoDB. The following argumentation makes sense, but it's likely they're using that. But I cannot really say if they're using a different system to store the messages. So that's why it's still an hypothesis. It's likely they're using a relational database, but I don't want, due to the fact they didn't disclose what database they are using, I'm not going to refer that. So it's likely that they have something like a message table and a conversation table, a relation one-to-many from conversation table to message table. So if you want to retrieve all the messages related to one conversation, you pick up the conversation ID, go on the message table and select all the messages that have this conversation ID. Now, the benchmarks that I'm going to show you are made possible thanks to Google Cloud, and this is the instance I have used. It's quite small because I want quickly to show the principles that I'm discussing. And if you want to replicate the benchmarks, you can go my repository on GitHub, and there's a step-by-step guide on the README that you can read and follow to replicate the benchmarks. Let's see, with InnoDB, that is database engine used by MySQL and Oracle DB. When we do insert with the UUID version 4, you see we start with 250 inserts per second. After dramatically drop after a few hours to 50 inserts per second. You see it's from 250 to 50 inserts per second. Why is that? What's wrong with that? It's because the way InnoDB is storing your data on disk is with the cluster index on disk. Essentially, every page that is stored on disk has an order. Like the page 0, for instance, contains the ID from ID 1 to rank 3. Page 1 contains IDs from 4 to 6. Page 2 contains ID from 7 to 9. So let's assume now insert row with ID 8 is coming. I have to do one IO, retrieve page 2, bring it in memory, and I insert inside page 8. Now, I don't flash immediately to disk. I keep page 2 in memory, hoping that the next insert will arrive and will fill page 2 before flashing to disk. In this way, I don't have to retrieve it again. This is called hot pages. I know what you are thinking is that you are thinking that the memory, the RAM is volatile. You are right, but database came out with a smart idea to avoid that you lose your data. I'm not going to discuss that in this talk, but let's just assume that they have a way to prevent your data loss. You can read more, like PostgreSQL it has a write-ahead log that they just act like a journal. Just write the statement that at date. I don't know, at that time, at that date, this insert came, and that's it. So I've just read it a small portion of data and make it consistent on disk. By the way, this is not the argument of this talk. So now I have in page 2, insert row with ID 9 is coming. Nice. I bring page 2. I don't have to bring page 2 in memory. It's already there. I write page 9, so I flash to disk. You see, I have 2 insert, but just 2 IO, 1 to read, 1 to write. Without this process that is called hot pages, I would have to retrieve again page 2, and this is not convenient. Now let's see with random ID, like with the UUID version 4. What is happening is that now ID 5 is coming. ID 5 is coming. ID 5 is in page 1. I retrieve page 1 and I keep it in memory, hoping to fill it. But I'm not going to fill it because the next insert is insert row with ID 3. Insert row with ID 3 is in page 0. So I go to disk, I bring in memory page 0, and I write row with ID 3. Now, hoping the next insert will arrive and fill one of the pages that already have in memory. This is not happening because now row with ID 9 is coming, and I have to retrieve page 2, bring page 2 in memory, and write row with ID 9. So you see, I'm doing a lot of IO just to read, and I keep this in memory. And the worst case scenario is that at a certain point, your memory will be full because it's just keeping pages in memory, hoping that the next one will come and fill one page. But this is never happening. So you just have the memory at a certain point, the memory full. A new insert is coming that wants another page, but your memory is full. So you start this processing of trashing that you have to understand what pages to flash to disk before retrieving another one. And this is super, 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 super expensive. So you see now for 3 inserts, I had 3 reads and 3 writes. That's not convenient at all. So, okay, Armando, that's your point, but what's the solution? For this specific problem, the solution is to use something like UUID version 7. In the case the OpenAI is using a relation database, I don't know why they didn't come up with this idea. The UUID version 7 has a timestamp at the beginning, the most significant bit, and after still the randomness in the others bit. Thanks to that, I kind of give some order to the way I insert my data. Because now what I'm doing is like, let's suppose that one page contains the insert, the rows in the last 5 minutes. So it's likely that when people are chatting with the chatbot, they, especially in the modern days, they're asking many questions. So it's likely that all those inserts will arrive in a certain time span. So it's likely that I will use a limited number of pages that represent that lifespan. So you see now I have quite not like sequential time. I don't have something like constant like as a sequence. If I would have a sequential ID, but sequential ID come with a cost. But still, you see the number of inserts that I have per second are kept on 250. They don't go like they don't drop down to 50 like before. And the Google Cloud offer a nice functionality where I can monitor my database and see how many reads are happening, how many writes are happening on the on pages. And you see with UUID version 7, I have mostly writes. With UUID version 4, I have a lot of reads and a lot of writes as well. That's now you can clearly see what I was telling you before. And I know what people are thinking is they are thinking, okay, PostgreSQL has not this problem because the way it stores pages is append only, so it doesn't try to keep the pages ordered on your disk. So just append, fill the page, flash to disk. But you remember, the point is always to reduce the searchable space. In this way, you do less I/O because you don't want to do a full table scan. So PostgreSQL still has to maintain B+3 structure that index your primary key. Otherwise, it's too slow to retrieve your data because it has to do a full table scan. And remember when I said that in a B-tree, one split can cause multiple split, and so multiple split equal multiple I/O. Well, this is the case. Once the B-tree is big enough and you have this randomness, you have many multiple splits happening in different parts of your tree, and you cannot monitor that because they are random. So you have one part to the left side that is causing multiple splits. After at the same time you have the right side that is causing multiple splits as well because everything is random. Database don't like entropy. You can see here that with UUID version 4, I have many reads and many writes. So with UUID, it's something like UUID version 7 with the timestamp in the most significant bit. I have many writes, but not a lot of reads. So you see the amount of I/O is reduced drastically. And let's see some data. With Postgres, with UUID version 4, they start from 400 insert and they drop down to 50 insert. This is the point. Eventually, this will happen because the B-tree has to be big enough. It's not like with DynamoDB that you can immediately see because you have to do those operation disk immediately. Is that the B-tree has to be big enough in this way that one split is causing multiple split in the entire tree, and so this is causing a lot of I/O. So I had to run the script for longer, like for 10 hours, and you can start seeing that it drastically dropped from 400 to 100. And remember that your database is in production, is always running, so you will see that. And with UUID, with the timestamp most significant bit, they are kind of kept constant. Why inserts are so important? If you want to scale, you have 2 ways. One is vertically, but vertically is limited. It doesn't mean adding more hardware to your server. And the second point is horizontally. And horizontally, you can do that in two ways. So you do sharding with a relational database, and this is super expensive because you add extra overhead and you don't need to do in your corporate or startup. Companies like Google can have to do it. So like there is YouTube did it. You don't need to do that. By the way, you still get benefit if you do database tuning, that you have to do less, you have to shard less and have less server. And the second way that is the most common one is having one master and multiple slaves that are the servers. But the point is that the master is the only one where you can insert, and the other servers that are the slaves are the only one you can read from. No, they are not the only you can read from the master too, but you cannot insert in the slaves. You cannot only read from that. So you have an insert in the master, and this insert is synchronized in the replica and the slaves. In this way, you can go and read from that. Now there is the CAP theorem, when to synchronize with what granularity. If you want more availability, you don't immediately synchronize less in this way. If you want a more consistency, you wait before returning. Okay, I did the insert. In this way, all the database, the replica are kept consistent with each other. So the database play on the CAP theorem for that. But this is another discussion, but it's another topic. And what about reads? You benefit reads as well. If you wanna select the message in the last 5 minutes, let's assume page 0 contains message with timestamp that likely covers the last 5 minutes. You have just to retrieve page 0 or page 0, page 1, but you see, you don't have to go to do something random that you have to retrieve multiple page. So even reads are getting some benefits from that. I'm coming here saying, oh, I'm the best engineer. And it's not true. Just people don't think about that. And they have many money to spend, and now it's cool to scale it, and no people pay attention to database tuning most of the time. But yeah, I found that Shopify, they have an article, it's called on this link, and they had the same issue. At a certain point, the insert were too slow, and they switched from UUID version 4 to UUID, that is the one with the timestamp in the most significant bit. And they reported 50% of decrease of insert statement duration. 50%. You know what does it mean? You cut the cost of 50% of your server or your database. That's a lot. So thanks to be here. Unfortunately, I cannot answer the question. This I will answer maybe if you wanna just let's get in touch, and this is my LinkedIn. Let's get in touch, and we connect, and you can ask on LinkedIn whatever question you have. Thanks for your time, by the way.